Hi everyone. So I wanted to use this video as an opportunity to work through a few examples of using standard reduction potentials to make predictions about chemical behavior. Um, so the basic idea here is that standard reduction potentials generally describe how readily a substance wants to gain electrons, and we can use a table of standard reduction potentials to make predictions, again, about chemical behavior. So your textbook has a table, a massive table here of standard reduction potentials. Those are going to be found in table 18.1 and page 821 if you have a full copy of the textbook. So I was going to work through a few examples working with standard reduction potentials. I'm not going to write all of their values up here, but I would say if you have a textbook or if you have a table of standard reduction potentials, you can follow along with these examples. So case in point, here is a question, which is if I try making an electrochemical cell, or just if I try performing this reaction, a reaction between chloride ions and zinc ions to make chlorine gas and metallic zinc, is that reaction spontaneous? Does it happen? Is that a favorable interaction? And I'll assert to you that you can make that prediction. Either you could have made that prediction by looking at delta G's of formation. You could do that just like would have done that previously. Or you can make a prediction by trying to calculate the cell potential that you would have for an electrochemical cell based upon this reaction. And we'll say that the reaction would be spontaneous if you predict that you have a positive cell potential for the reaction as given. So generally speaking here, the way to predict this is that if you have an electrochemical cell, the cell potential is equal to the difference in the standard reduction potentials of the cathode versus the standard reduction potential at the anode. And so if you want to decide whether a chemical reaction is favorable, if it's spontaneous, you need to identify which of these species is going to exist at the cathode. Look up that species' standard reduction potential. Figure out which species is going to act at the anode. Look up that species' standard reduction potential, and then find the difference between the two of them. So I would say take a minute, see if you can answer this question on your own. Otherwise, I would say pause it and take a stab at it. Again, what we're going to want to do is identify which of these is the cathode, which of them is the anode, and then based upon that, we can figure out the cell potential. So I'm going to work through how I would make that prediction. As again, we're going to figure out which one is the cathode, and the cathode, by definition, is where reduction is occurring. So I look at these two chemical species and I think, okay, which of them is being reduced? Which of them is gaining electrons? And I look at this and I say, okay, zinc is going from zinc 2+ to zinc neutral. So it's lost that 2+ charge, which means it had to have gained 2 electrons. So I predict that the reaction that happens at the cathode is the reaction of the zinc ion with electrons. Again, it's undergoing reduction, that's the cathode, and then going to zinc, which means that by definition the anode, or rather not by definition, but by contrast, the anode must be the reaction between chloride going to chlorine. And again, we might have been able to predict that ahead of time since the anode is where oxidation is occurring, and here the chloride is losing these electrons to make chlorine gas, and there are the 2 free electrons. So then I'm like, okay, I've figured out which of these is the cathode, which one of them is the anode. Now I just need to figure out, or I need to reference the table of standard reduction potentials and figure out what values I should plug in here. So the standard reduction potential for zinc is, if zinc is going to be behaving as the cathode, the standard reduction potential for zinc is minus 0.76 volts. And the standard reduction potential for chlorine is 1.3, I'm sorry, let me make sure I get this right, 1.36 volts, which is positive. So I predict that my cell potential here is going to be negative 2.12 volts. And that implies that this reaction is not spontaneous. We would predict that as written, the reaction would be a step down in terms of potential of 2.12 volts, and that is not favorable because it's a drop down in terms of electrostatic potential, and generally speaking, electrons like to go up in terms of electrostatic potential. So this reaction is not spontaneous, and in fact, I predict that the reverse process would be spontaneous, that if I were to place zinc in the presence of chlorine gas, it would donate electrons to the chlorine and form chloride and zinc 2+. So let me give you another example of a calculation like this, very similar. So, drop my marker. If I were to have a reaction between iron 2+ and silver ions to form iron 3+ and metallic silver, is this reaction going to be spontaneous? So I would say, yet again, pause the video, check your standard table of standard reduction potentials, figure out which species is undergoing reduction and which species is undergoing oxidation, and then based upon that identification and the value of the standard reduction potentials, we can predict whether or not this reaction is spontaneous. So, which species is acting at the cathode? Which species is undergoing reduction? Well, silver starts with a plus charge and it goes to a neutral state, so it has to have gained one electron in order to do that. So we're going from silver plus electron to silver neutral, and that means that the anode must be for the iron losing an electron and forming iron 3+, again with a free electron. So I predict that means that the iron 2+ to iron 3+ electrode, that's my anode, and the silver is going to be my cathode. And then all you need to do is check your table of standard reduction potentials and calculate the cell potential here. So for the cathode, for silver, that's going to be plus 0.800 volts. For the iron 2+ to iron 3+ electrode, that should be plus 0.77 volts. So the difference here is 0.03 volts. So this one, I would say it's spontaneous, it's just not very spontaneous. You're really not going to be able to get too much energy out of this reaction unless you had a massive amount of iron and a massive amount of silver, but even still, not that much of a push for electrons from the iron onto the silver, but still technically spontaneous. There's a general, okay, so actually I'll go do a few more examples here and then I'll see if we can come up for a general rule for predicting the direction for spontaneous change in terms of where things are laid out on the table of standard reduction potentials. Anyway, so let me give you one last series of questions based on this line of argument, or a similar line of argument. Suppose I gave you the following standard reduction potentials, and I want to have these up here. So I might have copper gaining 2 electrons and going to copper solid. I could also have tin, iron, zinc and aluminum. And I'm going to write all of these guys being reduced to their metallic forms. That's going to iron solid. This is gaining 2 electrons and going to zinc solid. 3 electrons going to aluminum solid. And I said I was going to give you the cell potentials here. So the cell potentials, these are all in volts. These should be plus 0.34 volts, minus 0.14 volts, minus 0.44 volts, minus 0.76 volts, and minus 1.66 volts. So this is might be a series of standard reduction potentials, and then based upon these standard reduction potentials, I've got a few questions. So here's a first question. Which metal is most easily oxidized? So, oxidation, oil rig, is describing the process of something losing electrons. So this question, which metal is most easily oxidized? Well, technically all of these reduction potentials are given as reduction potentials. If something is being oxidized, we're talking about how favorably does this go in the opposite direction. Again, all of these are written as such, as is, they're written in the form of reductions. In the opposite direction, we're showing the metal becoming oxidized, going to a higher oxidation state. And the question is, which of them do that most readily? And the answer here is actually going to be aluminum. I mentioned this in lecture today, that if you flip a reaction, you essentially flip the value of the standard reduction potential. So if I were to rewrite this reaction, aluminum solid going to aluminum 3 plus and 3 electrons, I would say that the potential drop for that would be plus 1.6 volts. And again, we're going to think that of a positive cell potential as being favorable in some way, or as being spontaneous or favorable. So this one is going to have the largest positive value if you write them all reverse. If you write them all as oxidation processes, then actually aluminum is the one that is the most easily oxidized. So for this, we'll choose aluminum. So there's that. Here's another question. Which metals can reduce iron 2 plus to iron? I guess I should be more accurate here. I'd say which of these can reduce iron 2 plus to iron solid, not iron. Yeah, I'll just say iron solid here. Iron 2 plus plus 2 electrons and going to iron solid. So I would say take a few minutes to see if you can predict this. Again, the way we'll generally predict this is that electrons like to move upwards in terms of electrostatic potential. So, for instance, if I have aluminum ions, they will tend to lose electrons and donate them to iron. Similarly, I expect zinc, if I place zinc in contact with iron 2 plus ions, zincs will very happily lose electrons, and then this sign will become plus 0.76, and then electrons will be accepted onto iron. So generally, I would say that these two metals, they will kick up electrons to iron 2 plus. So those are capable of reducing these. I saw this in a different textbook. I've never tried teaching this before, but I figured I will try it here. This is sometimes called the northwest southeast rule, is that metals that are on the southeast will reduce metals to the northwest, but not the other way around. I can't use aluminum ions to react with iron metal, but I can use aluminum metal to react with iron 2 plus ions. So for this, I would say that only zinc and aluminum are going to be southeast of iron. So this is the So that's one thing that you can use to check yourself. And then the last question I'll give here, if I were to write a balanced chemical reaction, if a balanced chemical reaction between, let's do something different here. Let's do zinc and copper 2 plus. So if I try adding zinc to a solution which has copper ions in it, does a reaction occur? Is this reaction favorable? Does it occur spontaneously? So there's a couple of ways you can do this. You can either apply the northwest-southeast rule and say, okay, copper is to the northwest of metallic zinc, so zinc will happily kick electrons up to copper. That would be a step up in terms of electrostatic potential. So again, you can either just use the northwest-southeast rule, or you can think about it in terms of the fact that going from an electron here, going upwards, that's a step up in terms of electrostatic potential, and we think of that as being favorable in some way. If I wanted to do it even more explicitly, if I wanted to actually calculate it, well, if I have a reaction here between copper 2 plus and zinc going to copper solid and zinc 2 plus, I would say, well, the reaction will be spontaneous if the cell potential is positive. So I could try calculating this explicitly by calculating the difference between the standard reduction potentials of the cathode versus the anode. As I've written this reaction, the cathode is going to be copper. Because as this reaction is written, copper is being reduced from copper 2 plus to copper 0. If it's undergoing reduction, that means that it should be the one that electrode will identify as the cathode. So for copper here, that's going to be plus 0.34 volts. And then for the anode necessarily is going to be zinc, because zinc is going from zinc neutral to zinc 2 plus, so it's losing electrons, hence it's undergoing oxidation, hence it would be labeled as the anode. And then the standard reduction potential for zinc at the anode is going to be minus 0.76 volts. So I predict here that the cell potential would be plus 1.10 volts. It's positive, so we predict that that is a spontaneous reaction as written. Okay, so those are just a few straightforward examples of how to utilize and how to interpret standard reduction potentials. Again, they are all written as standard reduction potentials. This calculation for calculating the cell potential is written explicitly in terms of reduction potentials. So a common tactic, I've seen people do this, I've seen this being taught in two different ways. One is this way, where you think about it solely from the perspective of reduction potentials. And then I've seen other people try to say, well, if you want to recreate this reaction, you need to keep the copper like this, because copper is going from copper to copper solid, and then you say, well, the zinc is going from zinc to zinc 2 plus, and in this reaction it's going from zinc 2 plus to zinc. So what I'll need to do is to flip this reaction, and that would make this positive. If I were to flip this reaction, then this would be positive 0.76, and then when I add those two reactions together, zinc going now to zinc 2 plus and 2 electrons, if I add this reaction and this reaction, I'll get this net reaction. So that's, again, that's if I add these together. And then if I add together these individual half reaction potentials, I'll get 1.1 again. And that's true, but you have to be careful if you want to also apply this reaction. Rather, apply this equation. This equation, again, is assuming that the values you're quoting are the reduction potentials. As soon as I flip this reaction, then the value I'm quoting here is now no longer a reduction potential, it's an oxidation potential. So, point being is you need to be careful, because here I'm trying to add two values together, and here I'm subtracting their difference. And basically I would say choose one method and stick with it. I'm going to stick with the first method, where you write everything in terms of reduction potentials. Even if the reaction that's occurring is not actually a reduction reaction for the anode, we understand it's an oxidation reaction. But in terms of calculating the potential difference, I'll do them both as reduction potentials. Okay, so if you have further questions about that, I'm going to do a couple more problems, or not a couple more, but I was going to start Wednesday's class with one more problem related to these, so we'll have an opportunity to discuss this in person, and then I was going to go on to some new material about how do you actually relate changes in cell potential to changes in free energy for a chemical reaction. And in doing so, we'll then be able to connect cell potentials, free energies, and equilibrium constants. They'll all be related to each other. So that's coming down the pipeline. Until then, I will see everybody later. Have a good day.